All right, it's 3 o'clock, 4 o'clock for you in AEDT, other times elsewhere. Welcome to to hour 21. So we're here. We have 2 hours today. We'll be speaking about generative adversarial networks. I hope it should be fun. Let's see. So we're entering the last week of the course, where you're basically touching 3 different areas: generative adversarial networks with me, sequential language models with Benoit, and then deep reinforcement learning with Sarat. So in this portion of the course, last week, we're taking more of a bird's eye view. Each one of these topics can be a mini course of a course or a course in its own right, and we'll just get a feel and a taste for it. Just some administration. So you do have the 3rd quiz coming up this coming Saturday. Then you'll have 1 generative adversarial question, 1 sequence model question, and 2 deep RL, or generally things taught in that unit question. In the unit on deep RL, you'll also do a bit of Markov decision processes, dynamic programming, Q-learning, and such. The 3rd quiz should be similar in spirit to the 2nd quiz, i.e. hopefully not too much work and not extremely difficult, and we'll also send a focus announcement. And I guess you have assignment 2, which is due very soon. Are there any questions before I start? No. Okay, so we'll be moving to the generative adversarial networks unit. And there's a few videos here, some of which I added quite late, so I assume you haven't seen them all. But there's just a few things to see. So the first of all is that this person that we see here on the right, I'll say it. I won't name it as a she or a he or a they. It's an it. It isn't real. It's generated, and that's kind of the context of this unit. Now, it's actually a very interesting unit. Beyond the fancy graphics, there's a whole bunch of mathematics that's taking place, and we'll be able to cover some of it. Now, I must also say that this is not my field of research. I have not published in generative adversarial networks. I've supervised a student and a half doing something on this, but more in an exploratory manner. So in a sense, it's kind of like you're getting a lecture here from your psychology professor that's filling into a sociology class, or maybe a botanist that's teaching you something about zoology, or some other silly analogy of that sort. So just keep that in mind. But I think that together we can explore quite a lot of this, and there's a lot to see. Okay, very quiet class. No comments? Nothing? No Monday joke? Anybody have a 1st of February joke? It's going to go on YouTube. If it's good, I'll read it out. I'll think about it for a second as we go. So there's 7.7 billion people in the world. Beautiful. I don't know. We need to cut out the white supremacist, the ISIS, I don't think is in there, and even just any old racist. But we still have quite a lot of beautiful people, and even those that have some flaws, we can look at the beautiful part. But the thing is, you see in this video, well, you can't see this video, but this video here, we can generate many more. Okay, so that's kind of generative adversarial networks, but there's a whole bunch of applications. So we'll actually start slowly going through a few terms and getting background on a few different things, and then we'll even you'll go on a website and play with GANs for a few minutes, and then we'll continue to more mathematics. So nobody has a 1st of February joke. We've had now about 45 seconds to deliver it. Fair enough. I mean, I'm bad at jokes as well. All right. So first of all, just some terms. Generative adversarial networks. Okay, so at least there's somebody said, sorry, can't think of anything. I mean, that's pretty good. I mean, it's on a funny scale, it's maybe not like killing it, but it's much better than the complete quiet on the line that we've had elsewhere. So that was good. Thank you. All right. So generative models. So we need to just touch a bit of terminology. So generative modeling is an alternative in the machine learning lingo to discriminative modeling. Okay. So let's just discuss this for a few minutes so we understand the concept. Okay. So in general, machine learning, you have kind of two approaches, two overarching approaches. One is the generative approach, generative modeling, and one is the generative approach versus the discriminative approach. Now, in the generative approach, what you do is you consider your data. Now, maybe your data is just X, right? As you'll have like an unsupervised settings, or maybe it's X, Y, you know, features and labels in a supervised setting, but it doesn't really matter. But the point of the generative approach is that you actually find out the probability distribution of X or the probability distribution of X and Y, if it's in the supervised case. Okay. Now, maybe you find out the distribution, or maybe you just develop an algorithm for generating samples from that distribution. Okay, and that's a subtlety we'll get to in a few minutes. But in general, that's generative modeling. Okay, so you've got your data, you assume that there is some underlying distribution behind there for the data, and you're actually wanting to find this out. I mean, statistical inference is generative modeling in a parametric setting, or maybe in a non-parametric setting. Kernel density estimation is generative modeling. This is very different than this guy, than the discriminative approach, where what you want to do is just find out the conditional distribution of your Y over your label or your response variable given X. Right. So logistic regression and classification and all the neural networks that we've done so far have all been discriminative. Okay. And we didn't have to speak about it too much because that was just given. You know, for a given X, we want to see what is the probability distribution of Y. We didn't even speak about the probability distribution. We just gave a point estimate, right? So we just said, hey, for a given X, what would be Y? Okay, that's the main thing a neural network does. Okay. And neural networks are not so great at giving probability distributions and confidence intervals like your more classic statistical models. But generative adversarial networks, first of all, the prefix generative, I mean, we are in the generative adversarial network lecture, come about because they are generative models. So before we move on to generative adversarial network, let's just look at a classic generative model called naive Bayes. And it's a classifier. So it does deal with a classification setting where we have X and Y. Okay, naive Bayes. This has nothing to do with generative adversarial networks, but it's maybe a good complement to your knowledge if you haven't seen naive Bayes before, and we'll just go through it quickly. So you just feel a generative model. Who has worked or seen naive Bayes? So this falls in kind of classic machine learning. It will often, so some have, great. So it would often be taught if you have a full semester machine learning course. It might be in the second, third, or fourth week or something like that. Okay, so and naive Bayes algorithms have been extremely successful for email spam detection. That was kind of the classic. Probably still used today. Okay. So the story that we have data, we have here n samples, right? Where you have a feature vector and a label, and a feature vector and a label, and you know, let's say that each feature vector is a D vector. So you've got D features. That's a similar setup to what we had before, and you've got K labels. I mean, for this to be interesting, K needs to be 2. Binary classification of the. So this is your typical setup. I mean, you know how to deal with such things with multi-layer perceptrons, fully connected networks, etc. Okay, but we're going to look at the naive Bayes approach just briefly. So what you do with naive Bayes is you assume a family of distributions P theta, where the parameters of the distribution are theta. Okay, that's kind of like what statisticians do. Right? You often assume there is some model for the data. Okay, so you assume some form. It's typically going to be a parametric form. So you actually assume something. We'll see an example in a second. Okay, and what you assume is that the XY tuples, XY pairs, okay, the features and the labels, okay, which you can also just write like this, okay, because this is just the probability of X intersection Y divided by P theta of Y, and then you multiply by P theta of Y. Okay, so this here is nothing but the definition of conditional probability. But what you make is an assumption. You make a structural assumption, and this is what gives this thing the name naive. This kind of ran over, but you could see this on the other notes. So this doesn't happen much in these lectures, but here, this is the equation we want. Okay, this is what you see on the website. Okay, so the naive assumption is that your probability distribution of the features given the label is separable, is independent. That the features are conditionally on the label, or conditionally on the label, conditionally independent. Okay. And there's a question: should it be a I in the subscript I rather than superscript indexes are features? Yes, yes, thank you. And there's a correction. Right, and this should be here. Thank you. I mean, this is for any old X. Very good. Yes. So this is not the I sample. Thanks for that correction. Well, I got it. You told me. Good. This is the I should be. Okay. And this is what you call the naive assumption, and this actually makes this thing tractable. Okay. By the way, naive Bayes has nothing really to do with the Bayesian method. It's simply that we're going to use Bayes rule. That's all. Okay. So what we do in naive Bayes is we're going to just aim for a classifier such that if we have a new observation, we can give a prediction for the label Y. And the way we're going to do it is very straightforward. We're just going to use this format. Okay, here it is without scratches, but with the I in the wrong place and the superscript instead of the subscript. But we're just going to use it with this format to do inference for theta. Okay. And here, by the way, also there's another typo. Sorry, this is a few typos here. This is theta hat and this is theta. It's all theta. Okay, so we have an estimated theta, but here's the estimate. The estimate will be theta hat. Okay, so once we've estimated theta hat, this is what we can do in the production when we actually use our classifier. When our email server tells us, "Hey, suspected spam." Okay, you get an email from your bank and says suspected spam, or what we'd call test time. Okay, when we have a theta, well, the predictor is simply going to be the thing that maximizes this thing. Now, in general, when you have such predictors, they're called maps. The map acronym is used in several places in the world, but in this context, it's maximum a posteriori probability. Okay, that's a map, maximum posteriori probability. So given some observed label, given some observed features X, we're just going to choose a label which maximizes this probability from the model. But the nice thing under the naive Bayes assumption is, well, now we can use Bayes rule. Bayes rule is nothing but the definition of conditional probability, and then you just flip the numerator. So you have X given Y multiplied by P theta of Y. And now we know this denominator is not a function of Y. So the thing that maximizes this thing is the same as this thing that maximizes this thing in the denominator. And then further, we can use the fact that we actually made some structural assumption about the conditional probability of the features given the label, and we assume that they're separable. And this, again, as I was corrected previously, this is xi, this is the i's feature. Okay. Okay. So that's a general idea of naive Bayes. And then what's happening is that typically we suggest specific probability models, some of which are very simple. So in a sense, the simplest one is what we call a Bernoulli naive Bayes, where we assume the following. We assume this guy here, that's the probability of xi given y. Now, what you see here in this is not yi. This is the index in the denominator. This is y and I. Okay, so there are parameters. So the probability pyi is the probability of a class y generating the term xi. Now, just to see how you would use this, say now if you have an email, okay, or in general text, what you could do is you can consider the bag of words. So you can take all of the words in the English dictionary, say from word 1 to word 40,000, and okay, so you've got these 40,000 words. Okay, many slots here. Okay. And then when you've got an email from somebody, you populate the words. Okay, but in this case, you don't populate the word count. Okay, you just populate how many are populated. Okay, most of them would be 0. And then based on this, it's easy to update these probabilities. Okay, so again, PYI is just a probability of class I either. And let's say there's just 2 classes. Okay, you'll have something like spam and not spam. Okay. So you'll only have for y, just 1 and 2, spam and not spam, but here you'll have 40,000, and you'll see what is the probability if some negative word or something like that says spam, and some of these will be pre-populated and some of these will be online learned. Okay, so this was something completely, that's kind of a tangent off from neural networks, really far from neural networks. But the reason that we put it here is just so you see this is a generative model. Now, why is it a generative model? Because we actually thought about the joint distribution of x and y. Okay, we actually learned the joint distribution of x and y. Okay. And that's a generative approach, in contrast to the discriminative approach, which we've done so far. Okay, and that's this phrase. Any questions, thoughts? No? Okay. So let's get to the second phrase. We're talking about generative adversarial networks. So there's a whole field called adversarial machine learning, and frankly, it's not so well defined. So adversarial machine learning takes different views and points, etc. Can be used for different things. But in general, if there's one thing in this field that somebody finds is kind of interesting, and this even made quite a lot of headlines a few years back. Let me actually refresh the page here, and you'll see this thing is this video. This is and the associated paper, which you have below, which showed how to actually 3D print a turtle such that effectively, no matter what angle you feed this turtle into a state-of-the-art network, trained inception network, or a network of that sort, it's going to think it's a rifle. Okay, we're not talking about a single angle, right? Because when we're training convolutional neural networks, we don't worry about the angle. These are just features that are kind of going into the network, and ideally the network filters sort this out. But this is kind of and this is in this paper. You might find this interesting. Again, not directly related to GANs, but this is maybe one of the most exciting adversarial examples, or one that has made headlines. There's a question. I don't understand the question. Sorry, what? A gun, a rifle. Oh, a rifle. Yeah. Just look at this video for very briefly. It's a quick video, and it just shows how you see the probabilities here on the left. Here are this. It always thinks it's a rifle. Okay, so that's adversarial in general. Okay, that's adversarial in general. That's a phrase. And now let's get to our candidate of today, or what we're doing, generative adversarial networks. We just put a bit of context into the meaning generative and adversarial. I see the formatting has come when I took it here. Oh, hasn't come wonderfully. Oh, here as well. Okay, so we'll just live with this. Okay. So this is what a generative adversarial network aims to do. In a generative adversarial network, we aim to have a generator and a discriminator. Okay, we're training two neural networks per se, a generator and a discriminator, G and D. Okay, so we're going to use these things throughout. Just moving up a bit, we can speak about data which is just X, as in the unsupervised case, or X and Y. Let's start with just thinking about the X case, okay? We'll just think about the X case for now, okay? So that's our setting, and then we'll move on to labels. So people can treat generative adversarial networks as unsupervised learning in general, but maybe the data does come with Y, with labels. Okay. And what we're doing is we're training a generator network and a discriminator network. Okay, that's first of all. I'm prescribing to you how in general a generative adversarial network works. And let's just see a bit of an illustration. So your network G, let me actually draw it like this. There are many different types of illustrations we can do, but this is one of them. Okay, so the network G is going to take noise. And noise is going to be some vector, which is actually never too big. You know, maybe there's 100 elements in there, maybe 200, maybe 1,000. I mean, of course, as a network scale, we'll need more, but not too big. So this is Z, and this is sometimes called the latent space. Although at first it's just going to be noise. And what G is going to create as output, what the generator is going to create as output, is a sample. Now, generative adversarial networks are not image specific. They can work effectively in any context, but a lot of the research has been in the context of images, because images are easy to look at and visualize, and are just one of the simplest, well, one of the most hands-on examples of high-dimensional data which we have. Okay, so this is an image. Okay, so the generator knows how to take noise and create an image. That's a generator network. And in a sense, when you're done with creating or training or producing or crafting a generative adversarial network, this thing here is what you're going to ship out. Okay, so for example, if you are working as part of a video game team, and you manage to train a generative adversarial network G, such that all that you need to give it is, say, you know, maybe something that's, you know, like 128 normal 0, 1 IID variables, for example, and it gives you an image of a character, and that character is completely bogus. You know, this is the thing you're going to ship out, and you're going to give to the video game team. And this thing is actually nothing but this G in here. This is nothing but a neural network. Okay, it's nothing but a neural network. Okay, so it has its parameters, which we'll call theta G. Okay, that's your product. Okay, so you can get an image that's like that and an image like that. So it's a mapping from IID variables to an image, or in general from the latent space to the image. Okay, from Z to the image X. Okay. That's kind of the output. The second component that you have in a generative adversarial network is your D. Okay, in the basic generative adversarial network is your D, your discriminator. Discriminate, to tell the difference between one thing or another. Okay, now D works on images. Okay, works on images X. But it can work on the, you know, on these fake X's in this kind of lighter blue, which come from the generator, or it can work on these slightly more robust good X's, which come from your image database. Okay, that's your data. Okay, this down here, that's your data. And They're both of the same size, the same format. So D doesn't know if it's getting this fake X or this real X. Well, it doesn't know, but it determines, and it tells you as an answer. Let's just keep it like that. It tells you one is real, 0 is fake. D is a binary classifier. D is a binary classifier. Okay, so a generative adversarial network in its basic form has the generator, has the discriminator, and the discriminator is a binary classifier, which is also a neural network, so it has its parameters theta d. Okay, and when I say parameters, I mean the weights, the biases, maybe a few more. Well, if it's convolutional, then the filter weights. If you're doing batch normalization, then the learned parameters of batch normalization, but basically the weights and the biases. Okay. And these two guys interact together where you start only with the image database. And you start, of course, with random parameters for G. And you start with, this is a training I'm speaking about, and you start with random parameters for the D. And they're trained together in a way such that after a while, D is fooled. D is the trainer, the discriminator is fooled. At first, when we start, the discriminator doesn't have, well, after it trained just for a few steps, doesn't have too much trouble to distinguish between a real image and a fake image. Because this thing is just going to look after a few iterations, just like some white noise. Okay, because we've passed white noise in through a network with rubbish parameters. But the system is going to feedback itself in a certain smart way, such that after a while, these things that are generated here look, the fake ones and the real ones are closer and closer to each other in the way they look. And then deciding between real and fake is going to be harder and harder. And eventually, ideally, the accuracy will be 50%, meaning like nothing, like as bad as a coin flip. Okay, that's the general idea. Okay, and yep, that's it. And here's another illustration taken from this blog post. It's not our illustration, but it basically does the same thing. Okay, so you've got your latent space and you've got your real samples, your latent space and your real samples. And after a while, this thing is wonderful. This G is wonderful, and the discriminator is really bad and actually doesn't know after a while. Oh, so maybe I made it. So there's a question, what is the definition of real being used here? Are we just looking for images that were in the set given? Yes, so real is here, yes. And just like was answered, thanks for answering. Yes, so real is here, right? So, you know, the real images are, the combination of the many real images are our closest approximation to the actual distribution P of X, okay? To the actual distribution P of X. Okay. All right. So how is this thing done? Well, it's done by constructing a game. The game theoretic foundations are not so important here, but let's just see the engineering feat of it. But there are also a few properties. Okay, so what we want is to create an objective such that G is forced to create better and better samples. Okay, and D is also training itself in a better and better way. Okay. Now, it's actually important in practice that we train. We'll speak about it towards the end, towards the next second lecture when we speak about Wasserstein GAN. But it's important in this classic. This is, by the way, this is called the vanilla GAN. So this comes from the original general adversarial network paper, which I guess I should have said, talked about immediately. the start. I'll just put it here. So this is this highly famous paper at the top by Ian Goodfellow and co-authors. Okay, and since then, so this is a new field, and since then there's been an explosion of GANs. So this is a very recent field. In 2014, the idea was released, and it's an extremely active field, as in deep learning in general. But this, in a sense, is kind of one of the biggest ideas in the past decade. And then there is a question: are G and D trained at the same time, or does G get practice well before G? So we'll speak about that. So there are different variants, but it's actually, as I was just saying, it's important that we actually train them somewhat simultaneously. So it's not that we can create this wonderful discriminator, let it sit, and then improve the generator. So we do need to do it at the same time. But the notion of same time has a few interpretations. We can do a few steps of this, a few steps in that. We can do in parallel. There are variations. We'll get to them in a few minutes. Yeah. Okay. So to discuss this, we need to introduce two bits of notation. So one we'll call P data of X is a probability distribution of the data samples. Now, as a probabilist and statistician, I'm kind of sickened by this. What's probability distribution of data samples? You've got data and you've got your model. Okay, but P data is kind of, you assume that the data comes from this real world. Okay, and then you've got this probability distribution, which is much more manufactured. It's a probability distribution of the noise. It can be ID Gaussians or ID uniforms. There won't be much more. Okay. And this D is a classifier. It returns 1 for a real image or 0 for a fake image in Lisa. So one sensible way to set a goal for the discriminator is say, hey, discriminator, we'd like you to consider all of the X distributed according to P data, and we'd like high values, I won't say maximal values, but high values of log of D of X, okay? So this just motivates you to have high values for the discriminator, okay? Because if something, you want D of X to be as close to 1 as possible, okay? Now, every time we take this noise vector Z, then, you know, this is a random variable, high dimensional random variable, not a huge dimensional random variable, a latent space random variable. And then we get this high dimensional random variable, G of Z. Okay, so we had here, this was Z, and here we have G of Z. G of Z is the deterministic transformation operating on the noise. Okay, D of Z. So the discriminator of D of Z is again going to be 1 or 0. What would we like D of G of Z to be, 1 or 0? What in general do we want? Do we prefer the 1 for D of G of Z, or do we prefer the 0? We prefer the 0, right? So the discriminator wants us to be 0. So then taking the probability distribution over the random Z values, so this is the random variable in the expectation operator, okay? If then 1, we'd want this to be high. So if we want a 0, we want 1 minus 0 would be 1. We want this to be high. So if we put these two things together, what we get is something that the discriminator, let's speak about the discriminator. The discriminator wants to maximize, and that's this expression. Of course, you could have put some weighting between the two, etc., but there's no real reason to do this. Okay, this V here stands, you could think of it as a loss function or a negative loss function because you wish to maximize it. You could think of it as a value function. We'll see value functions later in the week when you speak with Sarat about in a completely different context, in the context of Markov decision processes and reinforcement learning. Okay, that's it. So, oh, I see I flipped here, the G and the D, sorry, it doesn't matter. It's, one needs to come before the other, okay? This is not intentional, this is a typo. This flipping of the D and the G. Okay, so let's call it VGD. Okay, so this is GD, or DG, whatever. Okay, DG. Okay, so for any if we now stop at some point and say, okay, let's just say that this thing is fixed, or generator is fixed, what our discriminator wants to do is it wants to maximize this. It wants to maximize VDG. And what do we mean by max over D? Well, what we effectively mean is max over theta D, over all of the parameters of the neural network that define D, that define the discriminator. Okay, so a good discriminator can maximize this. Now, the generator, for any maximization that the discriminator has done, the generator wants the opposite. It wants exact opposite. It wants to minimize this. Okay, it wants to, and by this minimization, again, what we mean here are the parameters of the neural network of the generator, theta G. Okay, theta G, these parameters. So the basic GAN formulation is what we call a minimax game. Okay, in general, in game theory, this is called a minimax game. It's the context of game theory. We're not going to explore this so much here. And if we found parameters theta G and theta G that achieve a saddle point, and by that we mean that we cannot move, we have no incentive to move theta G anymore. There's some big highlighting. And we have no incentive to move theta D anymore. We have no incentive to move the green guy on the left or the orange guy on the right. Okay. Then this is called a saddle point. And then we said we've trained again. Okay. So in formulating a generative adversarial network in the basic classic formulation, there's an immediate game inside, and it's a game played by these two guys, where in games, and it's a zero-sum game, so if the generator gains, the discriminator loses, and if the discriminator loses, the generator gains. And the action space, for those of you that have done game theory of sorts, although it's not critical, but the action space is the set of parameters. And of course, you guys know that the parameters of neural networks are high dimensional in general, even in the smallest examples. You know, these thetas are in the hundreds of thousands or millions. Okay, so how is this achieved? The basic algorithm, and this is taken from the 2014, this is a snapshot. We have a few of these snapshots in today's lecture. So the basic algorithm of generative adversarial networks, which can still be used today, and these are toys examples that one can play with, and we will in a few minutes on a web-based app, okay, is actually not so complicated. It's simply saying, let's train both of these guys together. Now, let's just observe something. Consider these. We wrote this here theoretically as expectations. Okay. Now, of course, in practice, we don't have expectations, but we can approximate them by these are cross entropy losses. Okay, and we can approximate them from the actual data. But the second thing to look at is that imagine that you're now the generator. Sorry, there's a whole bunch of a whole bunch of kind of stuff here drawn on this, but I hope this can still make sense. But imagine you're the generator and you're solving this problem. If you're the generator solving this problem, this is fixed for you. I'm gonna scratch even more. Everything inside here is fixed. Okay, everything inside here is fixed. Now, notice that this guy is this guy, and the term on the left is actually irrelevant for the generator. Okay, only the term on the right is relevant for the generator, right? Because only this term has theta G, right? I mean, when you're trying to maximize, if I'm trying in general in mathematics, if I'm looking for argmax 5 plus let's do 5 minus x squared, Okay, argmax x, that equals argmax of minus x squared. Okay, that's, which is 0 here. Okay. There's a question. Are the D and G wrong way around? It should always D. Yes, they are. Thank you. Thank you. Thank you. Thank you. Good catch. Yes, yes, yes. This wouldn't work. This would just syntactically not work. D of G of Z. Good catch. Thank you. We'll fix. Complete typo. All right. So now let's go to the basic training loop and see what we do. So there's another feature here, and that adds to the that answers a question that I was asked before. Do we train them step by step or together? So there is an option to have this K steps, okay, where you do this is K steps. This is D training, okay. I don't think the colors I'm using are consistent in this, but just so you know, see different colors. This is G training. Okay, now you can do this D training for K steps. Okay, you can do K steps. In practice, the world's kind of moved away from these K steps, and even in the numerical examples in this original paper, they found that K equals 1 is possible, is the best. Now, what do we do in these K steps? Let's see. So what we do is we get a mini batch of M noise samples, which is just IID noise of your latent space. Again, you might have, say, if you're doing MNIST, you might have 100 variables in the latent space. If you're doing ImageNet, much bigger things, you might have many more variables. Okay, but that's a design parameter, how many things to have in the latent space. Now, there's notation here which we haven't seen, the noise prior, PG of Z. Okay. What they mean by the noise prior, well, by PG of Z, PG is actually the distribution of G of Z. Okay. I don't know why this says, this should say sample mini batch of noise samples from the noise prior. I think this G is actually a typo, but we will have the notation PGZ later because we just want to sample IID. And then you get a mini batch of M examples of your actual data. Okay, your mini batch M is again the mini batch size, and you update the discriminator by taking the derivative of this guy and this guy. Okay, and this you do using forward propagation and back propagation. Okay, there's a question. Yeah, so there's a question. Yeah, the PG of Z is the distribution of this guy, but here the way this is written, noise prior is this guy, right? So you can have the noise prior and your G is fixed. So when you're running this thing, when you're running this iteration, these K steps, which might just be 1, okay, if your choice was K1, this guy is fixed. This side of the network is fixed. You're now doing, for this binary classifier, D, you're just improving the binary classifier. Nothing really special about this algorithm. Another comment? Okay, I think it's okay. All right. Now, after we've done our step for D, let's update G. Well, here, as I said, when we look at G, the right-hand term is the only one that matters, not the left-hand term. And then we can do gradient descent. So D is fixed, okay? So now this D is fixed. This D is fixed, and I'm highlighting here. And we've got our mini batches of noise, okay? And then we're doing a gradient descent on the parameters of G. And that's it, okay? So that's the algorithm. I agree. This is a comment. We apply G to Z in the loss function. Yeah, I fully agree. So these things, as far as I see, are Z's. This is Z. Okay, this is Z. Fully, yeah, that's a. I believe so. Okay. So here's how this thing looked on the original paper. Okay. So what they did in the original paper is they looked at fully connected dense networks. I'm not sure exactly about the size, and they did it on data sets that you've worked with, MNIST and C410, also on the faces. Okay, and the thing is that all these guys here, fake. All these guys here, fake. I mean, C410 is such a non-appealing data set, really. And all these faces here, fake. Okay, and all these guys here, fake. And these guys on the yellow on the right, what they did is this 9 here, this is real, and it's the closest thing to this fake guy. And this 0 is the closest thing to this fake guy. This 2 is the closest root to this fake guy. The reason they did this is it's the big fear of anybody that's doing deep learning. You don't want your neural network to memorize the data, right? So, I mean, actually to us, this 8 kind of looks like this 8, but it's not, okay? It hasn't memorized it pixel by pixel. And this guy is nearest to this guy, it's certainly not, okay? That's some sort of heuristic demonstration that we haven't memorized the data. But keep in mind that, you know, when you're training a deep neural network, yes, you can memorize the data, but G of Z was actually never given the data anyway. Okay, so by memorizing the data, that would be the fear that inside these parameters of this generator, we've stuck all the data in there. It's potentially possible, but this wasn't memorization of the data. So this is an empirical demonstration that this thing kind of works. This thing kind of works. And of course, you know, now go back to, I'm sure most of you have looked at, for example, this video. This is now moving 5 years down the road. This person, which we see here on the right, is not a person. Okay. Okay. So let's go ahead and play with GanLab, and we'll do this going into the break, speak about it a bit into the break, and then a bit maybe after the break if needed. And then we'll go to the second part of the lecture. So what I'm going to do, I'm just going to stop the share on the iPad. We'll take a break in a few minutes, but you can also play with GanLab. So open your browser, if you can, and click on this guy on the GanLab. Now, hold on. You could look at this GanLab. This is not going to generate images. Our features here are going to be in two-dimensional space. Now, this is kind of a GAN version of the much more popular website TensorFlow. So, TensorFlow Playground. I'm not sure we use this in any of the lectures per se, but this is TensorFlow Playground. So now we're moving 2.5 weeks back when Benoit taught you about multi-layer perceptrons in general. So here we have data where you've got binary classification, you've got your blues and you've got your oranges, and the classifier learns this region, this nonlinear region, and you can make a network with neurons, etc. Okay, you've probably played with that. That's TensorFlow Playground. Okay, so the GanLab is a GAN version of this type of thing. So what we have here are just 2 features, okay, and we can we can choose different data sets. So this is the data distribution. Okay, there's these 3 built-in data distributions, or I can make my own. Okay, here's a data distribution in 2-dimensional space, 2 features, X and Y. Okay, in 2-dimensional space. Okay. If you were a statistical modeler and you'd say you'd look at like this data distribution that I've done, you'd probably model it by a mixture of 6 Gaussians, right? That would be one way of doing it. Okay, that's the data distribution. And what you've got here is a generator and discriminator. So as I'm going to hit train on this thing, I'm going to tell it to run, and it's running in my web browser. Okay. We're training two models, so we need a way to visualize the two models. Let me pause it for a second. I'll just pause it right there. So what we have here on the right are samples generated by the generator, these dots. And those lines are their gradient vectors. Okay, that's a bit too much information for just going ahead. And what we have in the background is a discriminator. So the generator and the discriminator are being trained simultaneously. And let's let this thing run. And what we want to do, and it's not showing, and it's running for many epochs, it's not showing us, it's just subsampling the epochs. Okay. What we would hope to get is a situation where the purple dots generated by the generator kind of overlap the green dots. Okay. And the discriminator has to continue to change because it's kind of training the generator. It's saying, hey, generator, hey, do like that, and then the generator knows how to all the time. It's adversarial. Okay, the generator is trying to be adversarial to the discriminator, and that's what's happening. So what you see in the background is the discriminator. Now, what you have here on the left is a manifold representation of the distribution of the generator. Okay, and I've made this maybe a bit difficult. Okay, so it's covering some of the dots, it's not covering all of them. This is hopping around. So let's take a break and go ahead and play with it a bit during the break yourself, and then maybe ask questions or discuss a bit later, or just enjoy the break. So in 9 minutes we'll continue. And there is a question just before we take a break. Would it be stable if the generator just clumped it all in one of the 6 green clumps? Yeah, but that would be mode collapse. Okay, so one of the big problems with generative adversarial networks is this mode collapse. So being stuck in one of the 6 green clumps and high dimensional images is like, you know, only being able to generate a very specific type of image from a heterogeneous data set. Ready? Okay, see you guys in 8 minutes. I'll be back actually in 3, 4 questions offline if you want. Bye.